Hello everyone, welcome to today's class. This is Teacher Simon taking you through AS Chemistry paper 9701-23 for May June 2025, and this is question 1. The chemical properties of an element are related to the electronic configuration of its atoms. Part A, Roman 1, give the full electronic configuration of a fluorine atom. Now you know from the periodic table, fluorine is in position 9. So if fluorine is in position 9, that means we can have 1s2, then 2s2, then 2p. This one has to be how many? 5. So there you have 2 plus 2, that's a 4, then plus 5, that will be a 9. So that is that. Then Roman 2, deduce the number of pairs of electrons in the second energy shell n is equal to 2 of an oxygen atom. Now remember, oxygen is in position 8. So its electronic configuration is 1s2, 2s2, then 2p. This one will be what? Will be 2p4. Yes. So you can see the principal quantum shell number 2, we look at 2s2 and then 2p4. Okay, so in the s energy orbital, we are going to have there are 2, and of course the p orbital has gotten how many electrons it must take in total. They have to be 6, right? Okay, so this one has 3 orbitals. Now here we have 1, 2, because there are 2 electrons in there. Then p, we shall have 1, 2, 3, then 4. So the pairs, we have this one here and this one. So meaning the number of pairs will be 2. So I'll put a 2 there. Then Roman 3, draw the shape of the highest energy orbital that contains electrons in an atom of calcium. Remember, calcium is in position 20, not so? It's in position 20. So it is 1s2, 2s2, 2p6, then 3s2, 3p6. Now those are 18. This is the electronic configuration for argon. And then we have 4s2. So the 2 then plus the 18 we have here, then it will make 20. So the highest energy orbital here is this one, the 4s. And an s orbital is spherical. So we just draw just a sphere like that. As simple as that. Then B Roman 1, write an equation to represent the first ionization energy of sulfur. First ionization energy, we look at the energy change when 1 mole of electrons is removed from 1 mole of gaseous atoms, okay, to form 1 mole of 1 plus gaseous ions. Okay, so I will have sulfur here. It has to be gaseous atom. Then we remove an electron from there, and then we get 1 mole of gaseous ions, gaseous 1 plus ions. You see that? So that is what we are having there. And the state symbols here, they have not told us the state symbols, but when it comes to these energies, you must put the symbols. So here we are looking at 1 mole of, this is 1 mole of a gaseous atom, then to give you 1 mole of a gaseous ion. You see that? Very important. Roman, to explain why the first ionization energy of sulfur is less than the first ionization energy of phosphorus. Now I'm going to first write the electronic configurations of these two. So phosphorus, we know it is in position 15. So we are going to have 1s2, then 2s2, 2p6, and then 3s2, then 3p, 3. Then sulfur 16. We are going to have this one here duplicated, but then instead of the 3 here, I'll put a 4. Okay, and then after that, I'm just going to consider that 3p orbital. Okay, the 3p orbital. So this one here has gotten 3 electrons in there. So we have 1, 2, 3. And then the same when we go to sulfur, this one is paired here. Now there are 2 electrons in here, okay, which repel each other. So here there is spin pair repulsion. So the fact that sulfur has gotten more protons, 1 more proton compared to phosphorus, that means its nuclear charge, okay, is greater than that one of what? Phosphorus. So you would expect the nuclear attraction for the electrons to be higher, okay, meaning its first ionization energy is supposed to be higher than that of phosphorus. But then, due to the fact that there are these 2 electrons in here, and there is what we call the spin pair repulsion, then there is a slight decrease in the nuclear attraction for these outermost electrons, and this one will outweigh the nuclear, actually the spin pair repulsion here is going to affect the nuclear attraction. So in that way, we are going to have the first ionization energy of sulfur being less than that one of what? Phosphorus. Okay, so we shall say that the spin pair repulsion, the two electrons in one of the 3p orbitals, in sulfur experience spin pair repulsion, which affects the nuclear attraction or I say maybe which decreases the nuclear attraction. Okay, let's just write that one, which decreases the nuclear attraction. The nuclear attraction for the outermost electrons. As simple as that. Actually, I will say which outweighs the nuclear charge, thereby decreasing the nuclear attraction. I think that is better. I can say which outweighs the nuclear charge, thereby decreasing the nuclear attraction. I'm trying to reorganize this such that we make a good statement here. So thereby decreasing the nuclear attraction for the outermost electrons, like that. I think it's better. The two electrons in one of the p orbitals in S experience spin pair repulsion, which outweighs the nuclear charge, thereby decreasing the nuclear attraction for the outermost electrons. So this makes the first ionization energy of sulfur less than that of phosphorus. Then Roman 3, arrange the three species. We have the fluoride ion, neon, and then the sodium ion in order of increasing radius. Now, when you look at all of these ones here, they have the same number of electrons, okay? But how about the protons? Sodium has gotten more protons. It has 11. It is an ion here. It lost the electron, but the proton is still in the nucleus. So it has the highest. They have the same electronic configuration. That means the same number of shells, okay? Then the protons. So this one has the greatest nuclear charge, okay? Greatest nuclear charge, the sodium ion, and therefore the greatest nuclear attraction for the remaining electrons. And this one will be having the smallest radius. So here I will have sodium, okay, there. And then the next one will be neon. It has 10 protons, okay. And then fluorine here, it has the less number of protons. So this one will be the last one here, okay. So in my explanation, I will say all have the same number of shells, or electronic configuration, okay, electronic configuration. Now this one here is the smallest because it has the highest proton number, and therefore the greatest nuclear attraction. So you can say sodium ion has the greatest nuclear charge and attraction compared to the fluoride ion with the smallest nuclear charge and hence smallest, or I can say lowest nuclear attraction. So that is that. So the greater the nuclear attraction for the outermost electrons, the smaller is going to be the radius of that given atom or ion.